Next we shall study about applications of op amp. In many applications, one may have to convert a voltage signal to a proportional output current. For this, there are two types of circuits possible. One is V by I, VI converter with the floating load, VI converter with the grounded load. The following figure shows a voltage to current converter in which the load ZL is floating. Since voltage at A is VI, so this is voltage to current converter with the floating load. The voltage at node A is VI, therefore VI equal to IL into R1, as IB is almost equal to 0, or IL equal to VI by R1. That is, the input voltage VI is converted into an output current of VI divided by R1. It may be seen that the same current flows through the signal source and load, and therefore signal source should be capable of providing this load current. A voltage to current converter with grounded load is shown in the following figure. Voltage to current converter with grounded load. So this is the circuit diagram. Here let V1 be the voltage at node A, and if you apply, actually that should be KCL. Writing KCL at that node, we get I1 plus I2 equal to IL, or I1 is nothing but VI minus V1 divided by R, plus I2 is V0 minus V1 divided by R, that is equal to IL. Suppose if you simplify this, you will be getting VI plus V0 minus 2V1 equal to IL into R. So from this V1 we can write V1 equal to VI plus V0 minus ILR divided by 2. Since the op amp is used in non-inverting mode, the gain of the circuit is 1 plus R by R equal to 1 plus 1 equal to 2. The output voltage is V0 equal to 2V1, that is equal to VI plus V0 minus ILR, that is VI equal to ILR, or IL equal to VI divided by R. As the input impedance of a non-inverting amplifier is very high, this circuit has the advantage of drawing very little current from the source. A voltage to current converter is used for low voltage DC and AC voltmeter, LED and Zener diode tester. Next we have a current to voltage converter. It is also known as trans resistance amplifier. The figure shows an op amp used as I to V converter. So this is the current to voltage converter. Since the negative input terminal is at virtual ground, no current flows through RS, and current IS flows through the feedback resistor RF. Thus, the output voltage V0 equal to minus Is into Rf. The resistor Rf is sometimes shunted with the capacitor Cf to reduce high frequency noise and the possibility of oscillations. Next, we move on to instrumentation amplifier and its application for transducer bridge. Instrumentation amplifiers are used in monitoring and controlling of the physical quantities in the industrial processes for measurement and control of temperature, humidity and light intensity. Normally, a transducer which can convert one form of energy into another is used to sense and deliver the required information in the form of an electrical quantity such as voltage, current or resistance. This signal is sent to the pre-amplifier stage for initial amplification, and after further amplification and processing may be passed to the output stages such as meters, oscilloscopes, charts, memories and magnetic recorders. The major function of an instrumentation amplifier is precise amplification of low level output signal of the transducer, and the instrumentation amplifier is widely used in applications where low noise, low thermal and time drifts, high input impedance and accurate closed loop gains are required. The important features required for an instrumentation amplifier are high gain accuracy, high CMRR, high gain stability with low temperature coefficient, low DC offset, low output impedance, low power consumption, low thermal drift, of course very high skew rate. The instrumentation amplifier shown has the feasibility of offering high input impedance and a high gain. So this is the circuit diagram of an instrumentation amplifier which we have just now discussed. The op amps A1 and A2 are voltage follower or buffer circuits acting as the input stage for each of the inputs V1 and V2. They have zero differential input voltage, that is VID equal to 0. Under such conditions, with the common mode signal equal to 0 and V1 equal to V2, the voltage across the resistor R is 0. The voltages at the inverting terminals of the buffers are equal to the input voltages. Since no current flows through the resistors R and R dash, the output voltages are V2 dash equal to V2 and V1 dash equal to V1 respectively. However, if V1 is greater than V2, then a current flows through the resistors R and R dash, and V2 dash minus V1 dash going to be greater than V2 minus V1. Therefore, the circuit will have more differential gain and high CMRR. The current flowing in the resistor R is I equal to V1 minus V2 divided by R. And the same current I will flow through the resistors R dash in the direction shown. The voltage at the non-inverting terminal of the amp A3 is R2 V1 dash divided by R1 plus R2. By using superposition theorem, we get V0 equal to minus R2 divided by R1 V2 dash plus 1 plus R2 divided by R1 multiplied by R2 V1 dash divided by R1 plus R2. Simplifying, we get V0 equal to R2 by R1 into V1 dash minus V2 dash. Since there is no current entering the op amp, the current I equal to V1 minus V2 divided by R which flows through the resistor R dash. Therefore, V1 dash equal to IR dash plus V1 equal to R dash divided by R into V1 minus V2 plus V1. Next, figure shows a differential instrumentation amplifier using transducer bridge. And we will continue. So that we will discuss hereafter. And if you continue to simplify the previous equations, we get V2 dash equal to minus R dash I plus V2 equal to R dash divided by R into V1 minus V2 plus V2. Substituting the values of V1 dash and V2 dash in the above equation, we get V0 is given by V0 equal to R2 divided by R1 multiplied by 2R dash divided by R multiplied by V1 minus V2 plus V1 minus V2. That is V0 equal to R2 by R1 1 plus 2R dash divided by R multiplied by V1 minus V2. By using a variable resistor R, the gain of this instrumentation amplifier can be varied. So, a differential instrumentation amplifier using transducer bridge. So, it's an application. In a resistive transducer, the resistance of the transducer changes as a function of the physical quantity under measurement, which is connected as one arm of the bridge with a small circle shown around it. Due to a change in temperature, the effective resistance of the transducer changes, and it is indicated by RT plus or minus delta R, where RT is the resistance of the transducer and delta R is the change in resistance RT. Next, we will move on to log and anti-log amplifiers. The following figure shows an inverting amplifier circuit with a diode substituted in the place of the feedback resistor. The op-amp inverting input terminal is held at ground level because the non-inverting terminal is grounded. So the circuit input current is I1 equal to VI by R1 and the output voltage is V0 equal to minus Vf, where Vf is the diode forward voltage drop. The typical diode forward characteristics is logarithmic in nature. So long as Vf is less than approximately 0.6 volt and If is less than 1 milliampere. Therefore, Vf is dependent on If, and the equation relating Vf and If is If equal to Is e power q Vf divided by Kt, where Is equal to the diode reverse leakage current, Q is the electronic charge of an electron, that is 1.6 into power minus 19 coulombs. Vf is the diode forward bias voltage. K is the Boltzmann constant. T is the absolute temperature in degrees Kelvin. So you can reorganize the above equation. So we get an expression for Vf as Vf equal to Kt divided by Q ln, that is natural logarithm of If divided by Is. Next we have basic anti-log amplifier. The anti-log amplifier is similar to the log amplifier with the diode and input resistor interchanged. The positions of diode and input resistance just interchanges. The circuit input current is now the diode forward current I1 equal to IF, and the input voltage is its forward voltage VF. The output voltage is V0 equal to minus IF into R1. Now substitute for IF, so V0 equal to minus IS R1 e power q Vf divided by KT, which reduces to V0 equal to minus IS R1 anti-lock